particular problem dealing with empirical formulas and molar masses and molecular formulas deals with nicotine. As many of us know, nicotine is found in tobacco leaves, cigarettes, has the following percent composition. We have carbon, 74.03% by mass, hydrogen, 8.70% by mass, and nitrogen, 17.27% by mass. So all of this should add up to be around 100%, because if we have all the elemental composition of the compound, then all of these numbers, percentages, should add up to be 100%. So it stands to reason the best way to work this problem is to assume 100 grams of the material. So we need to assume, this is the easiest way to do this. And we don't know what those subscripts are, so I'm just leaving those subscripts blank here. And I can put a question mark here, and this is what we're trying to determine the empirical formula, which is the compound written in the simplest whole number ratio. And then given that empirical formula, we can have some additional information. For example, if we know the molar mass of the compound, we can actually determine the molecular formula for the compound, which is probably more important than the empirical formula, because now we know the actual number, the molecular formula. We know the actual number of atoms in that particular formula unit for that particular compound. So here's the probably the easiest way to work this problem. There are other ways to work the problem. I've seen other ways that you can do empirical formulas, but since we are in percentages, since each element are given in percentages by mass, usually in grams, then, and these numbers add up to be 100%, so let's assume 100 grams of the material. So that's why we assume 100 grams of material. And then, if we assume 100 grams of nicotine right here, then we can proceed to say that in 100 grams of nicotine, we have 74.03 grams of carbon, 8.70 grams of hydrogen, and 8.70 grams of hydrogen, and 17.27 grams of nitrogen. Then we convert those quantities to moles of each of the respective elements, and then we divide by the smallest mole amount to get the empirical formula, and then to get the molecular formula, we compare the empirical formula, the mass of the empirical formula, to the mass of the molecular formula, and we can determine the actual number of atoms in the molecular formula. So that's the route we're going to take here. So if we assume 100 grams of material, then we got carbon. For carbon, we got 74.03 grams of carbon, times, we need to convert those to mole amounts. So carbon, the molar mass of atomic carbon is simply, and we need to, 1 mole divided by 12, I'm going to use 12.01 mole grams here. And you can see the grams using dimensional analysis, the grams cancel out, so we now have moles of carbon here. And that would, according to my calculation, that will yield 6.164 mole of carbon. And we do likewise for hydrogen and nitrogen. So if we do hydrogen, we assume 100 grams, we have 8.70 grams of hydrogen times 1 mole of hydrogen, which is equivalent to 1.01. I'm just going to use 2 decimal places. Grams. Again, the grams cancel, and we're left with the moles of hydrogen, and that would amount to 8.614 moles of hydrogen. And I like to go beyond the number of significant figures because in the end we're going to round off and we're going to drop the least significant figures, so we can get, according to the rules of significant figures, get the right number of significant figures. But I like, in these intermediate calculations, I like to kind of go over one so I can allow me to round off or do whatever I need to do to get the final percentages and so forth. So we have 17 for nitrogen. We have 17.27%, which amounts to, if we assume 100 grams, that will be 17.27 grams of nitrogen times 1 mole of nitrogen over 14.01 grams. So actually we're just dividing by the molar mass. I'm writing it like this, but if you look at it, we're just dividing each of these grams by the molar mass so we can get the desired quantity, the moles. And that will give us something like 1.234 moles of nitrogen. So we have that. So in order to get the empirical formula, what I like to do is to go from there. Over here would be C, 6.164 moles, H, 8.614 moles, 8.614 moles, and then N, 1.234 moles. Just get them from right here: 6.164, 8.614, 1.234, and then divide to get whole numbers, in an attempt to get whole numbers, we divide by the smallest mole amount, which is in this particular case is 1.234. And that should give us the empirical formula. Now we may have to do another step to get that, but let's see what that yields. That will give us C5, and that looks like it's going to be H7, and of course that's going to be N1. So now, so these are actually, we don't have to do that intermediate step. For example, if that was 1.5, then we would have to multiply each of these numbers by 2, maybe 3, to get integers, to get whole numbers. We always want to have whole numbers in the formula unit, and not something like 1.5, 1.3, or something like that. We need to get whole numbers. So the intermediate step, possibly, in this particular case, we lucked out. We don't have to do that intermediate step. But if we had, like I had a 1.5, we have to multiply each of these by 2. So that will be 3, that will be 14, and that will be 10. But in this particular case, we don't have to do that. Luckily, we don't have to do that. So now the next question is, so we got the empirical formula. So if the molecular formula is the molar mass of the compound, we want to determine the molecular formula. So let me erase. I might need some more space, so I'm going to erase all of this. Don't know, but it doesn't hurt to give us as much space as possible to do this calculation. So now we know that the empirical formula is C5, empirical C5, H7, N. So now we want to determine the molecular formula. Now the molecular formula is these subscripts multiplied by some multiplier. So in other words, the molecular formula is C5 times some number N times H7 some number N times N, and I'm going to put 1 there because that's understood to be 1 N. So we multiply each of these subscripts by some multiplier N to get the molecular formula. So how do we determine the molecular formula? Well, there are 2 ways we can do that. One way we can do that by inspection, and by inspection, since we know the molar mass is equal to, that should be given in the problem. If you work in a problem, then that should be given 162.23. And now grams per mole. All right. So that molar mass should always be given in the problem if you're trying to determine the molecular formula from the empirical formula, given the empirical formula. That need to be given. Otherwise, you won't be able to do the molecular formula. So now what you want to do now is we can do that by inspection, a trial and error, which is okay. You can do that by trial and error. Just assume N is an integer, of course. So you can assume N is equal to 1. So your molecular formula will be, if N is 1, will be C5, H7, N1. Just like the empirical formula. If this N was 1, lowercase n was 1. So therefore, we can say this will be 5 times carbon 12.01 plus 7 times 1.01 plus 1 times 14.02. 14.01 for nitrogen. These are the molar masses of each of the atoms, each of the elements. And that will give us, let me get my calculator out, 5 times 12.01. That's equal to 60 plus 7.07. That gives us 67.12 plus 14.01, and that's 81.13 grams per mole. And I'm going to call this, since N is equal to 1, I'm going to call this the empirical molar mass. Now we don't know for sure is that the molecular mass, the molar mass for the compound, based on the true molecular formula, But let's just, and that's why I'm calling that the empirical. This is the formula based on the empirical formula of C5H7N1. So let's assume N is equal to 2. All right, that would simply be 2 times that. And that will be equal to 162.26 grams per mole. Now we can see immediately that N is equal to 2 corresponds to the experimental, or the true molar mass, based on the margin of error. Now let's assume N is equal to 3. And your molar mass now would simply be 3 times 81, 3 times 81.13, and that will actually be 243.39. Clearly, this one is wrong. That doesn't even come close to corresponding to the true molar mass of 162.23. Clearly, the empirical molar mass is wrong. That doesn't even come close to that molar mass. This comes the closest within our margin of error to the experimental molar mass. So therefore, we conclude that N is equal to 2. So therefore, we multiply each one of these by 2. So the molar mass for nicotine would be C10H14N. N2. So that would be the molecular formula. And that's how, and these problems all work the same way. All of these problems pretty much work the same way. So that's basically how you would determine the molecular formula from the molar mass. Now, there's another way you can determine N. If you don't want to do the trial and error, you can determine N by taking the true molar mass, which is almost always given in the problem, 162.23, and divide it by the empirical molar mass, which is, in this particular case, would be 81.13, and you're going to get a number approximately equal to 2. So that's all you have to do. Divide the true molar mass with the empirical molar mass, and you got 2. So you don't really have to do the trial and error. Sometimes I like to do the trial and error. Sometimes I would just take the true molar mass and divide it by the empirical molar mass of right here, and we get a number really close to whatever the number is. And that particular, we determine 2, and then we proceed down that by 2, that by 2, and that by 2. And then if you look at nicotine, nicotine is a drug, and some people say caffeine is a drug. And this is found in tobacco leaves. You got the nicotine patches and stuff like that, cigarettes, and all this kind of stuff. And you can see a ball and stick representation of nicotine. And you can see that carbons are represented by the black balls, hydrogen is represented by the white, and nitrogen is usually represented by blue. So you can see the molecular formula here. We should have 10 carbons. We should have 10 carbons. Let's count. 1, 2, 3, 4. Let me go again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 carbons. We should have 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. There's a hydrogen back here. 9, 10. There's one back there. 11, 12, 13, 14. So we have 14 hydrogens and then 2 nitrogen. Now the organic chemists don't like to do this a lot. That's a lot of drawing and so forth. So what they've come up with is a structural diagram where now you can represent your nicotine in this fashion, which is much simpler than drawing that out all the time. So that is how we do the calculations for empirical formula. This is a basic calculation, given the empirical formula, given the percent compositions of a substance, calculate the empirical formula, and then given the molar mass of that particular compound from a separate independent experiment, that would allow us now to calculate the molecular formula. Now remember, the empirical formula gives us the simplest whole number ratio in that particular compound, in that particular molecule. But the molecular formula gives us the actual count of the number of atoms: 10 carbons, 14 hydrogens, 2 nitrogen. Your empirical formula is going to give you C5H7N. That's not the true number of atoms in that molecule. You have to do an additional experiment to get the molecular formula. So thank you very much.